Hi, my name is Maninder, and I'm a computer science and math student at the University of Toronto. I'm going into my fourth year, but I made this presentation in my second year and wanted to revisit it because I saw some of the ideas come up when I was taking a course in analysis. This presentation is on using continued fractions as an analogy to understand self-similar and infinite processes. A quick overview of what I'll be covering. There's two parts to this presentation, and if we have time, we'll get to part number two. I'll start off with defining what a continued fraction is. And because we should always work in examples, I'll give you an example of a continued fraction and how to evaluate it. And here I will show you a trick to evaluate it. But there's a problem with that trick, and that will be addressed when I'll give a more rigorous proof of how to evaluate continued fractions. So what is a continued fraction? They can be described as being fractions within fractions within fractions. So in this example, these values are actually, they aren't variables, they're numerical values. This continued fraction is finite, whereas this one is infinite. And the interesting thing is that the numerators actually take on value of functions, which is very interesting. And it is not obvious at all why this should equal to 10 of the tangent function, but it is. And because of this wide variety, we are going to restrict our definition to the simple continued fraction. Looks like this, and there are two simple rules to it. The first one is that the partial numerators have to be 1, and the partial denominators are just the natural numbers, so not including 0. A quick fun fact is that the first time mathematicians were able to prove that pi was irrational, it's not even transcendental, just irrational, was using this tan function, this expansion of the tan function. And this was relatively recently in 1760 by a mathematician named Lombard. So the point being, continued fractions are useful in math. To come up with an example, let's just start off with the simplest continued fraction we can come up with. So it's all ones. We write this down on a piece of paper. And now we ask ourselves the question, how do we make sense of this? At least for me, initially it was hard to wrap my head around it because of its self-similarity. Where does it start and where does it end? If we want to make sense of this, maybe we might ask, what does it equal to? And I'll give you guys some time to think about this. I'll start you off. If it's 1 plus something, we know it's greater than 1, but it's the other part of it is 1 over something. So this has to be less than 1. This fraction should be between 1 and 2. So I'll give you guys some time to think about this. Okay, so it was a trick question. It's actually hard. It's very hard to answer this question. And there's a trick that's commonly used in math competitions to evaluate these sort of self-similar objects. The trick is to let a equal to the expression. Once we do that, it simplifies our works a lot because we can leverage the fact that it's self-similar by replacing the denominator with a. We get this. From this rearranging, we get a quadratic equation, which we can solve using the formula. And it's safe to assume this is a positive value, so we can ignore the negative root. So, and we're done. It's equal to 1 plus root 5 over 2. If you think about this for a while, you might notice that this is actually equal to the golden ratio. And I find this very interesting because there was nothing to suggest the golden ratio would show up. But the evaluation of this, the simplest continued fraction, it just happened to be the golden ratio. That's a really interesting coincidence. Suppose you didn't know the trick, you wanted to evaluate it in your own way. The most natural way would be to consider the nth approximants. The way it works, the idea is that you truncate at finite points in the fraction and evaluate it. This table explains that. The index expresses how deep the truncation goes, and then the expression is what the truncation looks like. And then finally, these are the evaluations of it. You might say that, okay, if we go through this, use this way, the truncations are getting harder and harder to calculate because this is going to be a real pain to evaluate by finding common denominators and etc. As it turns out, it isn't as hard if you know the previous truncated value. So A5, I purposefully didn't write it down because I wanted to work it out. A5 is equal to 1 plus 1 over A4. Because this fraction, you can see that it kind of fits into its denominator. So we can kind of use a self-similarity here again to reduce our calculation. So A5 is 8 over 5. And this is very useful because if we know the nth truncation is P over Q, we can calculate the n plus first and the n plus second. And if you stop here just to think about how these are related to each other, you come up with two very important observations. The denominators of an plus 2 is the sum of the previous two denominators, and the exact same thing is true about the numerators. Take a look at this. Q plus P equals to P plus Q. P plus Q is equal to 2P plus Q. So I want to ask, is there any sequence that we know that follows this pattern of the sum of the two previous terms? And I think most of us know this is the Fibonacci sequence. And as it turns out, the nth convergent is actually just the ratio between two consecutive Fibonacci numbers. And from the previous slide, we showed that this fraction is equal to the golden ratio. So informally, what we just showed, which I just find so amazing, is that the ratio between two Fibonacci numbers tends towards the golden ratio, which is it's just a fact that maybe some of us know, but haven't seen a proof of. And this is a very weird proof because we are relying on these weird continued fractions that nobody seems to talk about in math. So yeah, we successfully related Fibonacci numbers to the golden ratio. Here are some exercises if you guys want to try it out and use the trick I explained before. I made some of these questions up, and it would be great to know that somebody actually tried them out. So there's a problem with the trick. It assumes that the expression converges to start with, and we know that not all expressions converge. If we assume that they do and use this trick, we might come up with some nonsensical values. And the good thing is that the trick is still valid if the expression converges. But the question is, does this expression even converge, the 1 plus 1 over 1? And suppose we are able to show it does converge. That's it, right? We can use the trick? Not exactly. There's another problem with the continued fractions. So consider this. So let's evaluate. So this is a sequence of equalities, which we can see there's a contradiction because it seems that this continued fraction, 2 over 3 minus 2 over 3 minus 2 over 3, is the exact same over here. But that would mean that 1 is equal to 2, which doesn't make any sense. But at every single point, so this point, 2 divided by 2 is 1. This is going to be 1 then from the previous fact. And this is going to be 2 divided by 3 minus 1, which is 2. So 2 divided by 2 is 1. The same thing is true over here. So there's something wrong here. It seems to be that this converges to do two different values, which doesn't make any sense. So clearly, infinity isn't something to casually meddle with. So qualitatively speaking, the problem are just 3 dots at the end of the fraction over here. They ask the reader to make some assumptions about infinity, which could be different from person to person depending on how they approached math or how they were exposed to infinity. Another way to understand this would be that the dots cause a loss of information. This is because if you look over here, you can always see that at the end of it, there's always this 1 and a 2. So we would expect there to be two at the end of infinity, right? So that might be why it's different. And Here is a very silly example. I like examples, and this is a nice one. So here it goes. Let's say a person says that this series is equal to 10. We know that's not true, right? This series is equal to 1. Then you ask him, how did he come to this conclusion? He said 10 is equal to 1 plus 9. You agree? Then he says it's equal to half plus 9. Says he can split the second half into 2 quarters. And then the second quarter into 2/8. And then he just puts the dotted lines and says, therefore, it's equal to 10. So this is kind of what is going on, at least one of the things. To fix the problem, we need 3 things. We need to define 3 things. We need to define an exact process for the infinite continued fraction, so we know how to evaluate it, right? The second thing is we need an initial seed value, because it seems that the different seed values may result in different evaluations. And we finally need a definition of convergence. And we will use, so everyone knows what we are talking about when we say something converges. And we are going to use epsilon delta. So now we are finally ready for the simplest proof of, or not the simplest proof, it's epsilon delta proof, so it's not the simplest. Okay, so we define the seed as being 1 and define the process in a recursive formula using this. And we can all agree that the limit of this equals to the continued fraction. So thing to note, this is not the only way to define it, but as long as we all agree, this is a valid way to define it. What was epsilon delta again? It was for every epsilon greater than 0, there is an n such that x is greater than n implies that the limit minus the x term is less than epsilon. Okay, and then we let epsilon be arbitrary and then choose an n, right? So what is an n? I'm not going to give you the n right away because it's going to seem like magic, so let's come up with the n. So we're going to use some of our pre-knowledge to figure this out. Epsilon x plus 1 is the error of the x plus 1 iteration. So we assume with our pre-knowledge that every iteration is going to get better. So this fraction is going to be less than 1. And as a matter of fact, if we can prove that this fraction, which is actually just this fraction over here, if it's less than 1, we can use something like the comparison test to actually show that it converges, right? So this is all we need to do. So let me just move my face out of the way so we can refer to these facts. We need one more fact, which is specific to the limit, which is the golden ratio. We need this identity. Phi minus 1 is equal to the reciprocal 1 over phi. And numerically, they look like this. So let's get started. So consider the ratio between the nth error and the n minus 1 error, which should be less than 1. That's what we're going to show. Using the definition of the process, we can a sub n is equal to this. And using the identity over here, if we move 1 to the other side, we can sub that into phi. So we get this, right? And now the advantage of this is that we reduced the n index to n minus 1. So it seems like there could be some sort of cancellations. And we clean it up like this, the ones, so these two ones cancel out. And I won't go through the details, but this is very simple math. We can cancel it out and we get this. So these two cancel out. We are left with this expression over here. And because at every single point, we already observed that it's going to be greater than 1, we can bound this even further by 1 over phi. So we showed that this ratio is less than or equal to 1 over phi. By a comparison test, we can come up with a geometric series that has a ratio 1 over phi, and by comparison test, we can show that it converges. But I'm not going to use comparison test. I'll actually just go through a different approach. I mean, technically we're done, but I'll just show you this way. It's less than 1 over phi. We're rearranging it, denominator, the n plus first error goes over here. Now I want you to think about what this is saying in words. It's saying that we can bound the nth error with the nth plus and with the previous error, as long as we multiply it by this ratio 1/5. So we want to reduce this all the way down to 1, right? Because a sub 1 is a very simple number, it's just 1. So we can bound this by keep on reducing the indexes at the cost of one factor. This is why you get this inequality over here. At the cost of n minus 1 factors, we can actually just put in a sub 1. A sub 1 is 1, phi minus 1. Using the identity over here, we get 1/phi is this. So remember what we wanted to show. This is what we wanted to show. This was less than epsilon, right? So this is less than phi to the minus n. So we just choose n to be negative log phi, log of e sub phi, which is actually greater than 0 whenever epsilon is less than 1, which is not an issue because we always consider when epsilon's tending towards 0 anyways. And we are done. Now, what we just showed was specific for 1 plus 1 over 1 plus 1, etc. As it turns out, if we start to generalize this a little bit more, if we let it, instead of being 1s, we could let it be equal to a's. So we can denote it like this, just for ease. This also converges. And the proof is, we can use the exact same proof. The only thing that changes is the identity. The identity in the bottom right corner that we were using for phi. And generalizing it even more, it doesn't even have to be the same values as long as there's a repetition. So ABC, ABC, ABC. We can use the exact same proof. The identity would change, maybe a little bit more messier to manipulate the symbols, but this also converges. And to top it off, if we have any continued fraction whose tail end repeats, so the starting can be anything it wants, as long as the tail end repeats, the fraction also converges. And these fractions are called periodic continued fractions, and they always converge. And they are, if you study them, they are related to the quadratic irrationals, which is all the irrational numbers that can be a root of a quadratic equation. And if you study this even more, you can start to solve some important Diophantine equations using continued fractions and these quadratic irrationals. They have an interesting relationship with each other. So we fixed the problem, right? We used the exact definition of a process, which was an iterative definition. And we also initialized a seed value for the process, which was 1 in this case. And finally, we use an exact definition of convergence using epsilon delta. I want to make a comment on convergence, is that sometimes if you're studying it, studying math, and you come across something to do with infinity, you'll start to notice, especially in upper years, is that the author might stop and take some time just to give you some definitions and theorems about convergence. And there's a reason why, because with different convergence theorems or definitions, you might end up with different values. So it's just an interesting observation. So to summarize, what did we learn? We learned that the 3 dots in mathematics, they cause us to assume some unsaid stuff, which can be different from person to person. We saw how infinite processes can be defined iteratively and how the seed value can affect the process. And finally, we had a definition of convergence. So specifically to this talk, we learned how to use epsilon delta on iterative objects or recursive formulas, which is something you might not have seen. We used this interesting technique of considering the ratios to find delta, or n in this case. And finally, we saw that consecutive Fibonacci numbers tend to, the ratio tends to phi, which you might have known, but this is an interesting informal proof of that statement. And I was thinking about, just a quick disclaimer, I was thinking about how this is actually useful for us as people who study math. And I don't think it is very useful. because if you ever study a textbook, all the processes already infinite, anything to do with infinity already take into consideration all these issues. For example, the Sierpinski triangle. It isn't a vague idea in geometry or fractals or whatever. It actually has a step, it has a concrete steps you can use to generate it. So we are never going to encounter an issue in math textbooks where there's weird contradictions. But what we have now is that we have tools so that if you ever come across a video on YouTube that makes like absurd claims that 0 equals to 1, we now have the tools to dismantle their argument and feel good about ourselves, because YouTube can no longer cause us any pain. Yeah, thank you for listening. And if you guys have any questions, I'll be happy to answer.